The subject in week 6 is hypothesis testing. This is the foundation of real statistics. Everybody that's using statistics in their job is using some kind of statistical test that has this idea as like its parent. Okay, everything is coming from. Everything we've done has worked up to this, and everything you could ever study in statistics is a derivative of this right here. And what is a hypothesis?
It's just an educated guess.
Educated guess. I mean, that's perfectly good words. So somebody has made an educated guess about something, and we can test it. Just like when we did the confidence intervals in week 5, there was a confidence level associated with that interval. And that confidence level that we gave to that interval, maybe it was a 95% confidence interval. And that meant we were 95% confident that, let's say, mu was between 2 and 10 for whatever, for something. Now let's try and understand a little more clearly what this is saying to us. Think about where the 2 and the 10 would have come from. The 2 and the 10 would have come from where? How what are they built out of?
The most right, I would say.
What is it built out of?
Well, it's the bell curve thing.
That's where this is coming into play. The 2 and the 10 would have been the sample mean is where our starting point would have been. We would have subtracted some error to get down to 2. We would have added that same error to get up to 10. So this confidence interval is directly related to the sample that underlies it. Okay? And all we did was just do one sample. We took a sample. We were able to get a sample mean. We did some other stuff, and we got this error term. It allowed us to construct the 2 and the 10. And what it's saying to you, this 95%, what it's saying to you is that if you did this sampling 100 times, then you can expect the mean to really be in between these two numbers 95 times out of 100. It won't be true every single time that you have captured mu in here, but it will be true an awful lot of the time, and we're able to quantify how often that is. And that 95%, its only place where you see it is in that error term. In fact, within that error term, the only place you see it is in that first number. Remember, the error term was equal to the product of two numbers. And this one was like a standard deviation, and this one was like a scalar. And it just scaled the standard deviation to be bigger or smaller depending on how confident you want it to be. So if we want it to be 95% confident, and let's say our degrees of freedom is just whatever, then this would have been a number that was pretty close to 1.96. You remember that? Remember when it was z sub alpha over 2 and we were like, oh, every single time it's 1.96. That was because you had the luxury of not having the degrees of freedom.
Yeah, that was the percentage or something.
Yeah, because we would have put 95% of the area in between two numbers on the normal curve. Here, this is about a mu. This is a confidence interval about a mean. So you wouldn't be doing this on your normal curve. It would be on your t curve. Okay. The reason it has to be done on the t curve and not the normal curve is because you do not know the standard deviation. You do not know the population standard deviation, sigma. All you knew was S, the sample standard deviation. So this turned out to be S over the square root of n. And what did it get scaled by? It got scaled by the number t sub alpha over 2, where this 95% was equal to 1 minus alpha. One minus alpha was what was in the middle. That meant that the rest of it had to have been alpha, because 1 minus alpha plus alpha is 1. The area under the curve is 1. So that if this is the part in the middle, then that means the two tails, when you add them together, add up to alpha. So then just one of the tails is alpha over 2. Ringing a bell? Draw a picture for you.
A lot of bells ringing in my ear as I say that.
The picture explains it all. This could be a picture of the normal curve or the t curve or whatever. They both pretty much have the same shape. Right? And if I put, let's say, 95% of the area in the middle, there's 100% of the area under the whole thing. I mean, that's a stupid statement, right? Maybe not stupid, it's an obvious statement. Underneath the whole thing is 100% of the area. Duh. So 5% of the area must be what these two add up to. Then each of them by itself is just 2.5%. Right? So in this picture then, we would have had alpha being 5%. 1 minus alpha would be 95%, because 1 is 100%. And if alpha was 5%, then alpha over 2 is this 2.5%. And this is the big idea of how the confidence comes to exist. And the number we are always interested in for that scalar is this number right here. This is our scalar. It is a t sub alpha over 2, or it is a z sub alpha over 2, depending on which curve you're looking at. Here's our code. Mm-hmm. Okay. So, the error is just the product of these two numbers. The limits of the confidence interval exactly come from the underlying sample, because it has to get constructed out of the sample mean and the sample standard deviation along with the size of the sample. And this guy over here just makes this number bigger or smaller depending on how confident you want to be. Understanding this mechanism, we need it in order to proceed. Because we're going to build this idea from this. So this was just last week. This was the confidence interval. What other elaboration do we need to understand this clearly? mean, there's no doubt that it's, I mean, it's challenging. But is there any part of it that could be elaborated on that might help you? Which part of it's the stickiest part? Like, help me to know where it's hard.
For me, I always forget a step. Well, I wrote it down in my notes, but yeah, I have to remember the calculator, do the square root first, and then.
Yeah, but that's all procedural.
Oh.
I'm wanting to make sure that we understand the conceptual part, or else this is not going to really make any sense.
What's the 2 and 10 again?
I just made them up. They're the lower limit and the upper limit
Okay.
of the confidence interval.
And then the mu is the mean,
The mu is the population mean, a number that we can never know, right? So maybe this is I mean, think of anything that almost always happens between 2 and 10. The price of gas around the world, the average price of gas in the whole world is mu. Okay? I don't actually know that number. But I can be 95% confident that no matter where I go in the world, it will be between $2 and $10 a gallon. Okay? If I went to France, it's going to be up here. If I go South America, it's going to be down here. But I'm 95% sure that it will always be between here and here. And occasionally, very slim occasion, I might go to, Luxembourg or something, and it's $10.50 or $11. Or I might go to Venezuela, and it's $1.50. Okay? So it can be outside of this, but the majority of the time it won't. How would I have gotten the 2 and the 10? I would have taken samples of gas prices all over the world, not everywhere, but a random sample from everywhere. I would have found the sample mean. That sample would have also had a standard deviation associated with it. Think about it. I'm going to be getting gas prices from Saudi Arabia and Germany. I mean, they're going to be very, very different prices. So there's going to be a big standard deviation. My sample mean is just whatever it is. It's just a single number. But I'm going to add and subtract the error. The error is nothing more than this standard deviation. It's actually the standard error once it's divided by square root of n. It's like a standard deviation. It's same difference. But I'm multiplying this by another number just to make it a little bit bigger or smaller, usually bigger. Because where does this guy get its authority? Here. This is the only place where this comes into play. Is the degree of confidence you wish to have in your result being correct boils down to this scalar. It takes the standard deviation and makes it bigger. It widens the interval. The error gets bigger. It widens the interval until finally you'll be right 95% of the time. Let's say I want it to be right 100% of the time, then this would be 0 and this would be infinity. I would be right 100% of the time. Yeah. That would be a very wide interval. So as the confidence level goes up, the interval has to get wider and wider. The only way that that's happening is if the error is increasing more and more and more. The only way the error is increasing more and more and more is because this number is changing. That one's not going to change. It's just whatever it is based on your sample. But this one changes with your level of confidence. Okay. What we can do So briefly ignoring the fact that there was the confidence interval about a proportion. Let's just focus on the one about a mean because it's easier to deal with. It's more familiar feeling. Then the statements that we have about this confidence interval is this. This is our sample mean minus the error, sample mean plus the error, and mu is in between. This is nothing more than the statement. This is nothing more than what we studied last week, just the confidence interval. Let's suppose that for whatever the confidence level is, let's suppose that this was one of the times where mu actually did come out in between these two numbers. For somehow or another, we were able to calculate the population mean, and we found that we were right. It really did come out in between these two numbers. Let's make that supposition. We need to do some algebra. I want to do some algebra. What I want to do is, instead of having mu here in the middle and all this other stuff on the sides, let's see if we can rearrange this so that it's just this confidence number that's on the outsides and all the other symbols are in between these inequalities. Riley, this is right up your alley because it's from algebra. We should be good at this, right? Yeah. What this all boils down, I mean, look, I'll tell you, the most confusing part of what you're looking at here is that it's crazy looking notation. If it just said 2 minus 10 less than or equal to a 50 less than or equal to 1,000 plus 1, you would have no problem rearranging it. Okay, so don't let all this decoration and stuff mess you up. This is just a number. Now I can move it around with algebra just like I could any other number. And all of this is just a number. So since these two things are being added together, I should use my additive inverses to move this x term into the middle. I can subtract x bar everywhere. On the left side, x bar minus x bar, it's gone. Here in the middle, it'll say mu minus x bar. Here on the right, the x bar will be gone. So I'll be off. I'll have a good start. Now I'll have minus t sub alpha over 2 times s over root n less than mu minus x bar less than t sub alpha over 2 times s over root n. Now we've got this difference here in the middle. This is the difference between the population mean and the sample mean for whatever sample we're looking at. Okay, this is good. The idea that we're having by doing this is that if I can get all of these, the S, the N, and the X bar, if I could get them in between here, in between these two less than and greater than symbols, then what it would say is it would say that the minus t sub alpha over 2 is less than all this stuff is less than the positive t sub alpha over 2. That would tell me that the thing in the middle is one of these scores, just like a t sub alpha over 2 is one of those scores on the curve, on the t curve. That's going to be useful to us because in order to test someone's hypothesis, we're going to be able to collect sample data. So we'll be able to make a number x bar. We'll be able to make an s and a root n. And they're going to make a claim about what this is. And we're going to stick their claim in there and compute, it'll be a number. And then depending on how confident we want to be in the results, that will tell us what this and this should be. Just like our level of confidence in this thing being true only came from the t sub alpha over 2, the level of confidence that we'll have in their assertion being correct will also be tied up in this t sub alpha over 2. Now, the only thing that's left to do here, well, there's two things left. The very next step is to if I say this right here, s over root n, all of those symbols, that's a number. I have this number times this. Let me just divide by that number everywhere, right? No? This is a number. It's being multiplied by this. I'm going to divide everything by this number. It'll cancel. I'm going to divide here, here, and here.
Oh.
That way it'll cancel there, and that'll put it in the middle. So I'm going to divide by s over root n. I'm going to divide by s over root n. I got to use parentheses there, okay, or else it doesn't mean anything. Or else it means something, but it's just ambiguous. Now these s over root n's will cancel, just like the x bar minus x bar canceled. And if you look, we nearly have it. I'm going to rewrite it here, but we have minus t sub alpha over 2 is less than, all of this is less than t sub alpha over 2. So this string of inequalities, these things on either end, they are just t-scores. So it must be the case then that this is also a t-score. And if up here we were assuming that, hey, this worked and we really did trap the mean in between these two limits, then it would still be true down here. All we did was some true algebra. So then it would tell us that if mu really did live in between the limits of your confidence interval, then you would also be able to make this same statement. That if mu lived where your confidence interval said it should live, like 95% of the time, for example, if mu really did come out up here, then it would also satisfy this. Like this statement would still be true. Okay. So if somebody made a good educated guess as to what mu should be, then I should be able to go out and get a sample, calculate an x bar, calculate a standard deviation based on that sample size, stick in their good educated guess, crunch this number, and then for whatever we would have gotten here and here that was associated with 95%, this number that we would get need necessarily also be between that figure and this figure. Make sense? Okay. I only want to make one more change to what we have here. I just want to multiply everything by -1. Because the ordering of this up here is more traditionally written the other way. It turns out it really doesn't matter. It's more traditionally written x bar minus mu. Well, I can make that happen. If I multiply this by -1, it'll become positive. This will have to flip its direction because it's an inequality. If I multiplied this by -1, then it would say minus mu plus x bar. But minus mu plus x bar, I can just write that as x bar minus mu. And then this would have to flip its direction because it's an inequality. And then this one would become negative where it's positive right now. Okay? And if you did all that and then simplified, the only change would be that it would say this. Because all of the arrows changed direction. They all started pointing that way. And so they all started pointing to the one that had the negative t sub alpha over 2. Well, that's exactly what this says right here. They're all pointing towards the negative t sub alpha over 2. This is an important observation. The observation is that this is the confidence interval. We could conclude that good educated guesses for mu would have to satisfy this statement. I do some algebra, and the very same thing can be said down here. Good educated guesses for mu would have to satisfy this statement.
So that statement's the same thing as the top one, technically?
Technically,
It's just redone, reworded.
yeah. It's just recast in a different light. Instead of being a statement about mu, because this one up here is useful for saying, here's where mu lives. This one down here is useful for saying, if somebody took a shot at a guess of what mu should be, then it should be between these two numbers, if they are correct. We end up calling this number, x bar minus mu over the standard error, is called the test statistic. It is called the test statistic.
No, the test statistic, like a little more than a hypothesis kind of thing?
It's called the test statistic because once someone has made their hypothesis, we can then compute the test statistic to understand how likely they are that they're correct based on a sample. We don't actually know what the population mean is and may never know, but we can go out and collect a sample and feed in a degree of confidence that we want to know that their estimate of what mu is true. And that degree of confidence will dictate what these two numbers out here would be. So if I had a very high degree of, if I said you can be 99.99, let's say, imagine if the interval, imagine the normal curve or the t curve, and we had, let's just say, the 95% here. Then this number would be t sub alpha over 2, and this one would be minus t sub alpha over 2. Okay? If I compute the test statistic based on what the number they gave me for mu, everything else is coming from me. Mu is coming from the person's claim that they're making. Then, if that number comes out here in the middle, they have a good claim. If that number comes out in one of these tails, that's a violation. That means if I took that mu and backtracked up to here, it would not be coming out in between this and this for my confidence interval. So valid claims will end up living in between the plus and minus t sub alpha over 2. We have a little bit more of a rigorous way to know if we would keep that claim or reject it, but this is the idea. We cool with this?
So far.
Great, great.
Kind of getting.
It comes from the confidence interval. That's the main thing so far. We built this thing, the test statistic. It comes from the confidence interval. But now what we need to compute this is somebody has to make a hypothesis about mu. And then we can compute that thing. So here is the notation and procedure. Someone will make a claim about mu. And we will have two cases: the initial hypothesis and the alternate hypothesis. Initial and alternate. Neither of them are equations. They are just names, and then the equation part will be over here. The initial hypothesis is always, without fail, always a statement about equality. Mu is equal to something. The alternate hypothesis uses an inequality. Mu is less than whatever, or mu is greater than something, or mu is different, just using the not equal symbol. Let's stick with the gallon of gas idea, right? So maybe some really brilliant economist comes in and says, well, I've done my studying, and the population mean for a gallon of gas worldwide is, 450. I don't know. I mean, it's like 3 something right now. You got to think about Europe and all that. I mean, should I do $3? You want to guess? Here, do you want to do it instead of the economist?
The economist doesn't know shit.
Okay, 450.
Actually, Europe is pretty screwed on gas right
Yes,
now.
they are. That's why everybody in Paris is riding around on scooters and has little tiny cars.
Because in Europe, before the war happened and everything, basically all of Europe stopped producing all their own stuff and just started buying from Russia. So when Russia invaded Ukraine, they didn't have any more gas no more.
So this is how I would write my hypothesis test. This is how I would start it. This is how everyone would start it. We make some initial hypothesis. The economist is claiming that the real average price of a gallon of gas worldwide is $4.50. But Riley's thinking that sounds high. It should be lower.
Like 4.
Okay. You think it should be lower.
Let's go with 4.
So our alternate hypothesis is that mu is less than 450.
I'm going to say it's not lower. I'm just hopefully hoping for the best.
So we have someone that made a claim. This is their claim. Alternate to that claim is just, this is as easy as it could get, right? It's either it is 450 or it's less than 450, right? Okay. This is setting up the hypothesis test. This is step 1, okay? The initial hypothesis always is an equal symbol without fail. Down here, the alternate hypothesis could be a less than, it could be a greater than, or it could be a not equal symbol.
Is that the equal thing with the slash through?
Yes. It just depends on what they have asked you to check as to what symbol gets used here. Also, later on in the process, we have to come back to this symbol to know how to make our final conclusion based on what's right there. Okay. This is step 1. Step 2 would be to calculate the test statistic. So if I come back here to what we had, I plopped down these numbers 2 and 10. If 2 and 10 are the limits of the confidence interval, then what's the number that's right in the middle?
2 and 10? Of 2 and 10?
Yeah, 6. That means X bar is 6, and the error is 4.
Well, is the error because it's 4, 6 from 2 is 4, and 6 from 10 is 4?
Yeah. So I must have, in the sample that I did, I must have been able to calculate that the average price of gas of all the places I checked had an average price of 6, and this number, 4, would be computed from here. Okay. Now I can backtrack and figure out what, I didn't write down what S and root N were and all that, but if we were 95% confident, then I can get a grip on what this number was. Right? I'd have to say, oh, I checked 100 places or whatever, but then I could go get a degrees of freedom and I could actually write down what this number was. I just look it up on the calculator. And then if I knew this number, given that the error was 4, I could eventually calculate what that S over root N must be. So to keep with all these numbers, I'm going to need to do that. Let me get the software open. Yeah, this is really powerful stuff. Like if there's like a paper written, let me say it like this. If someone has having to do a study about the efficacy of some drug or a vaccine or whatever, they're doing this, hypothesis testing.
So the hypothesis testing isn't like obviously isn't like the exact definitive answer kind of thing. It's just more of a very strongly estimated guess kind of thing.
Strong enough to go to court and defend a billion-dollar company type of strong.
Mm-hmm.
Much, much stronger than someone saying, in my experience, it's like this or that.
Unless you're just trying to prove the hypothesis, whether that is in that area, the low and the high, but you're trying to make
We'll come back more to the word prove in a while. But
the word prove in statistics is pretty broad.
That's the whole deal with statistics. Is you don't really prove anything. We talk about the degree of certainty. I can only prove that there's very few things that you can prove that are going to happen. Those are the things that have a 100% probability of occurring. Well, that's not very many things. If I toss a coin, the only thing I can prove is that it's going to hit the floor. But even that is not 100%. It's just really, really close. It's practically 100%. Time might stop between now and when the coin hits the floor, and it just never hits.
There's a leprechaun come around to the
Yeah, leprechaun comes around and catches it and takes it off, and then I never see, and then never touches the floor again, and that would be a very rare event, but it's possible. Okay, so let me open up my StatCrunch.
I don't really like certainty in these situations. Like I don't like to use the word certainty and or I guarantee it or anything as well.
Yeah, there's very few guaranteed events. Really, if any at all. So I was saying that my error was 4, but we had a 95% confidence. If I just pretend that my N was 100, then that would make my DF be 99. And putting 95% of the area here in the middle, gives me that T sub alpha over 2 of 1.9842. Okay, this means that 4 must equal to 1.9842 times S over the square root of 100. That's a one variable equation I can solve for s, right? So evidently, based on all this that's going on, it must have been that when I collected my sample, that s was huge. So it must have been that s was 20.159. If I had done better at picking my numbers to begin with, then that standard deviation wouldn't be so big, but whatever. Okay. Because you got to realize what this is saying. This is saying I went somewhere and I found gas that was, I mean, I guess, maybe in the middle of Death Valley, at the hottest part of the day during the zombie apocalypse, yeah, I guess there is $30 a gallon gas. But at any rate.
I don't think in a zombie apocalypse they'd be selling gas. I think.
You need to
Somebody's going to be selling. It'd probably be more than that, though. All right. So 20.159. It doesn't matter. We have some numbers. So I've got that S is 20.159. We had that X bar was 6.
So X bar is the mean, technically.
Sample mean.
Sample mean.
S bar is, or not S bar. X bar is the sample mean. S is the
That's the standard deviation.
sample standard deviation.
Sample standard deviation.
Yeah. Sigma is the population standard deviation. Because we don't have this number is the exact reason we're having to use the t-curve instead of the normal curve. Okay. N was 100, and that is everything we need to calculate our test statistic, right? Because our test statistic was the difference in the means, which is just a deviation, compared with this standard error, which is just like a standard deviation. That means that this thing here is really not any different than a z-score. The z-score was the observed minus the mean over the standard deviation, and that's what this is. Right? We are just assuming that the mean is what they said it is. Here's what we observed, and this is like a standard deviation. It's really just like a z-score. That's why this is what's seeming very familiar to us if we made that realization. Let's compute this test statistic. Okay, so X bar 6 minus 450, which is what the assertion that mu would be. 450 over 20.159 divided by the square root of 100, which is just 10, and I got to put parentheses around that right there. So when you go and do your computation in your calculator, you will need to put the numerator in parentheses. It's like I have some parentheses with a bunch of stuff in it, and then there's a divide symbol. And then there's a new set of parentheses with the denominator. Okay? Because if you don't put those parentheses, then it will mean something different to the calculator. Okay? I do not want the calculator to think that I mean this. Which is what it will interpret if I don't have parentheses around the numerator.
This is why you want us using that Google calculator.
Yes. Okay, so let me get this number. 6 minus 450 divided by, open parentheses, that thing. I get 1 Why is it not writing? I get 0.744. I should do 4 decimals, so there we go. Okay. I can know the outcome of the test already. There's another step, but the way that we developed it, we would know what this means. This is a t-value on the horizontal axis of the t-curve. If I were to remember what that t-value was that I got, let's see, it was 1.9842. So here's our picture. 1.9842 and minus 1.9842. Those were the numbers associated with being 95% confident, right?
Those are the ones outside of the mean, right? Like with the greater than, less than, what we had, right? You know how I said like a t sub alpha over 2? That's that number?
That's that number.
Okay.
Yeah, this is t sub alpha over 2. And this is minus t sub alpha over 2. And when we did our test statistic just then, we got 0.7441. So it's like right there. This is our test statistic. And what did that statement say that was written down here at the bottom that I said that we decided was exactly the same as what was at the top? It was like, if this one at the top was true, and the mean really was in between those two limits, then this one at the bottom would be true. And the test statistic would be in between the two numbers. So this is a picture of what a good educated guess looks like. Because it comes out in between these two numbers. So 450, it is totally plausible that 450 is the average price of gas worldwide. That's based on our sample that we collected. Because all these other numbers, like in the course of computing this, we had to collect a sample. It contributed some numbers. They had to make their guess. It contributed the mu. We calculated it. It came out in between these two things, which only come from the degree of certainty you would like to have. Right? I mean, I can say I only want to be 50% certain, and these two numbers might squeeze together such that this is finally on the outside of it, in which case 450 would not be a good enough guess. So the quality educated guesses, the ones that we like, the ones that are very plausibly true, have this result. They come out in between. Get it? Okay. Did we prove that the average price is $4.50? Absolutely not.
You just know that it could be 450.
Right. And we know and we have a number, 95%. We are 95% sure that it could be 450. Right? If somebody went out and collected 100 samples of this gas price data, and they always stuck with the 95% confidence, then 95 times we'll be right with this guess, 5 times we'll be wrong. Okay. The formal way to finish the hypothesis test is that we take this number, 0.74. I mean, technically, the test is done.
Was that all step 2?
Yeah. No, step 2 is actually not over. I mean, so here is step one, right here, doing that. It's easy. Step two, find the test statistic, and then do this next thing I'm about to describe here. We found the test statistic. It was just making this computation. As an intermission, we decided, hey, we already know what the outcome of this test is because we understand where the test statistic came from. But the formal way everyone does it nowadays is to take this test statistic and go into the T calculator and compute the area in the table past the test statistic. Just like the just like alpha over 2 was this area in the tail past T sub alpha over 2, what we now have is a test statistic. There's our test statistic. And we are going to go into that T calculator and calculate the area in the tail past the test statistic. And that area is what everybody wants. And that's what everybody knows. Everybody in the game knows how to interpret that area. It has a very useful interpretation. The name of that area is called the p-value. It's a capital P dash value, p-value. One day, before long, you will be reading some kind of research paper in medical related or in nursing or whatever. It will be talking about p-values. And it'll just be rambling, it'll just be talking, and it'll suddenly say, and our p-value was whatever. And they'll have no other context. But everyone knows how to interpret that because they did statistics. Now that area in the tail past the test statistic is the p-value. Here I drew it, to the right. Okay. It would not be in the tail if my suppose my test statistic was over here, then going that way wouldn't be in the tail, right? Okay, yeah. So you always want to go into the tail past the test statistic. 0.7441. Let's finish this drawing here with some areas. So 0.7441. What's up?
So you go past the test statistic. You always go to the right of it.
If the test statistic is a positive number,
You go to the right.
I would need to go to the right.
Negative is the left.
Yeah, so that way I'm getting the tail. All right. So, 0.7441 and greater than so the area in the tail past the test statistic, 0.2293. Do 4 decimal places. 0.2293. That's the area that goes all the way to positive infinity. What was the area that's just past 1.9842?
What's the area past it?
Yeah, 2.5%. 0.0250. Let's write that down. Okay. I have to make one change here. I should have had the foresight for this. So when we said that right there, less than 450, then that is us saying we are doing a one-tail test. A one-tail hypothesis test. Not two-tailed. The not equal symbol would be two-tailed. If it's less than or greater than, it's one-tailed. And the picture that I've got going here is a two-tailed picture. Okay, it's two-tailed because I would have 2.5% here and 2.5% here. The real picture for a one-tailed test should just have the body of 95% and then the one tail of 5%. So I will need to go back to my, the confidence interval is always two-tailed, okay? But for the hypothesis test being one-tailed, I need to go back and get a new number here that has 5% of the area. Or really, I don't even need that number. Here, watch. That's the beauty of doing it this modern way. Don't need that one. What we do need, though, is to say that 1 minus alpha, our confidence level, it was 95%. This means that alpha is just 5%. And I can just consider an area right down here of 5%. That's also written 0.0500. And the picture is still the same picture as it was before in terms of which one overlaps which. Because if we're going to call this red shaded area, we're going to call it the p-value. And this part here in this tail, that's alpha. That's alpha. And I guess the more fancier name is that it's the significance level. A lot of times in your homework it's going to say significance level, other times it will just say alpha. 1 minus alpha was the confidence level. Okay. And this picture is still true, right? Because this is like 22% of the area, and that's just 5% of the area. So of course this one sticks out way past it. And we are calling that red area the p-value. And the next thing I'm about to say is going to be the most important part of today's lesson. So we already knew what having this as our test statistic meant. It meant that it was a good, educated guess. The proper interpretation of the p-value is as follows. The p-value is the probability it's a probability. What is it the probability of? It's the probability that we would mistakenly reject Judge. That we mistakenly reject the initial hypothesis. Hypothesis testing, it's all about, you've got your initial hypothesis, you've got your alternate hypothesis, and our choices are reject the initial or do not reject the initial. We would say fail to reject. And those are the only two choices. It's kind of like if you go to court, there's not like guilty, not guilty, or innocent, right? They never prove you innocent in court. You're just guilty or not guilty. So the initial hypothesis, we are only going to be able to decide, do we reject it or do we fail to reject it? The p-value tells us the probability that if we decided to go ahead and reject, it would be the probability that doing so is a mistake.
So to reject the initial hypothesis,
Yeah.
that so is that like 22.93% technically?
There's a 22.93% chance
That we would,
that if I said to that economist that you're wrong, it's not 450. This is the probability that I'd be wrong.
okay. I'll take those odds.
That's way too high of odds usually.
Really?
Yeah. Think about how people want to be. For you it might be okay, but if this is about if it's a different context altogether, then maybe we'd want a much better likelihood, right?
Like 0.01 kind of
Yeah.
stuff.
Like if it's about a drug or something, and we want to ensure, we want to know for, if somebody comes in and says this drug is safe, I'm gonna want this to be low.
Yeah, because at that point you're saying, oh, I'm 77% sure that this will work.
So that would be someone making. Someone could say that in the course of creating a confidence interval. But at some point, in order to conduct the hypothesis test, someone has to flatten that to 100%. They say, this is the answer. The answer is $4.50 a gallon. We stick it into our test statistic, we can get this number. That number corresponds to this area. And this area has the interpretation that it is, if I just default to reject H0, it's just like my job, I always reject. Bring it to Mark, he will always reject it. How likely is it that he will be wrong when he does that? That likelihood is this number, the p-value. If this number is too high, then it would not be smart for us to reject, because the chance that we're going to be wrong is big, right? Like if this number, if someone said, hey, the drug is safe, and if someone said, hey, the drug is safe, and that was our initial hypothesis, then if this number starts to get big, and we decide to go ahead and reject, then there'd be a big probability that the drug really was safe, but we said it wasn't safe. Right? So, in other words, if this number starts to get too big, then it becomes too risky of a proposition for us to go around rejecting stuff. In which case we would say, hold on, let us fail to reject. If you fail to reject, it's not proving the initial hypothesis true. You're not saying that, hey, yeah, they're right. This would be a situation where we failed to reject that claim that it was 450. All that we are really doing is saying, you know what, we don't have anything contrary to the claim that the price of gas is 450. We will fail to reject.
And this is how a test.
This is how stuff is done.
Of drugs.
Yes.
This is why so many people die from those drugs.
No, this is why they live. This is why they don't. This is why they don't die.
Well, yeah, actually, that is true. That's wild.
Yeah.
Put some numbers in and then like, all right, I guess it'll work.
Yeah. Well, it doesn't. It becomes not a guess anymore, right?
Right.
It becomes something measurable. You can know the probability of someone's assertion being true or not, based on a sample that you collected. You can understand how it will perform on the whole population based on just this sample. And that's statistics. This is what it is. This is what it's about. And every statistical test that you would ever learn after this is some kind of permutation of this process. All right.
I really hope they'll be passing drugs with a 22% chance it'll fail.
Lord, no. No. So this is not a 22% chance of failure.
Oh.
Read the part in blue again. This is, if the hypothesis test was the initial, if the initial hypothesis was that that the average number of people who experience, horrible, if the average, so if this is the average failure rate, on the average, it fails to cure. It fails to help 5% of the people, and alternately, we could say that percentage is greater. If alternately it fails to help more than 5% of people, then maybe we don't want to bring the drug to market. Right? Don't worry about if it's safe. So the claim then would be that, you know what, this drug, so like here's the manufacturer's claim, only 5% of people can't get help from this drug. And then the CDC, they come down here and they'll construct this hypothesis test with this alternate claim to try and discredit what this says. All right, then they'll go through, let's say they got all these same numbers. And so the CDC is sitting there looking at this as their p-value.
That's the
Okay?
probability. P-value is probability value.
It's the probability, yeah. They've got this as their p-value, and they're saying, okay, the probability that we come back here to the manufacturer and say, you know what, you are wrong. Our study found that more than 5% of people were not helped by your drug.
You would have
If we did that, we would be wrong 22.9% of the time. The CDC doesn't want to do that.
the CDC would be wrong.
The CDC would be wrong.
Okay.
The CDC would be saying, hey, manufacturer, this is not true, and that statement would be wrong this often. So in that event, the CDC would not be telling that to the manufacturer because this number is so big. The only way that they would be saying this to the manufacturer is, guess what? If it was smaller than 5%. Because that would be small enough of a chance.
So tell them, oh, actually, you're wrong. It's this.
Yeah. Because the probability that they would be making a mistake to reject that manufacturer's claim, the probability that the CDC would be wrong is a small percentage. It would be less than 5%. And so they would feel safe in going toe-to-toe with the drug manufacturer and saying, you're not coming out with this. Okay. When we come back from break, we are going to work some problems. Just like last week, it'll be the last half of the homework first, and then the first half last.
It says I get to redo my quiz. I had my grandma's funeral, and so we got back and it was late, and I was like falling asleep trying to do it. So I didn't do too good, but can I do it today?
Yeah, for sure. All right, let's take 10.
Okay.
fuck.
So we'll start with number 6. Oh, that's a good question for us. You have hypertension if systolic's above 120. That's what it says. That's a well-known cutoff, in other words.
Well, yeah, I've always said, if it's like below 140, maybe normal,
Yeah, so there's,
like medically wise.
yeah, I mean, so you're pre-hypertensive between 120 and 140. Yeah.
Yeah.
Okay. So, but normal and healthy. Below. Okay. We go out and collect a sample of 100 blood pressures of people. And we get a mean of 124.5, and we have this standard deviation 16.3 36793. We'd have to use all the decimals places that they give us on these problems. Assume a simple random sample has been selected. This is just telling us, so your sampling technique has to be just random. That's what this is. The significance level is 10%. That's alpha. Okay? Alpha is 10%. They want us to test the claim that this sample of 100 blood pressures came from a population that was at least pre-hypertensive. So look at what's going on. The sample mean that we got was above 120. So someone might be thinking, hey, yeah, you did a simple random sample. So it's going to have some people whose blood pressure is high. It's going to have some whose blood pressure is normal. But we might be thinking that your sample is messed up. Either it wasn't actually random, or it's just one of those rare cases where you did a random sample but wound up with too many people in your sample that had high blood pressure. And so we'll be able to use the hypothesis test to know if our sample data came from a population whose mean was equal to 120 or greater than 120. So we're doing hypothesis testing about a mean. The initial hypothesis is always about equality. Alternately to that, it would be greater than 120, but the initial hypothesis would be that it's equal to 120. Okay. This is our initial, this is the setup of our hypothesis test. This is the first step. So we can word the claim in a weird way. Here the claim that we are testing is that the sample came from a population that was not normal and healthy. And so the words of that claim get kind of embedded in this H0 and H1, right? Ultimately, we will either reject H0 or we will fail to reject H0. If we reject H0, then it would be in favor of H1. We're not proving that H1 is true. It would just be that we have proof that H0 is probably not true. In which case, we'd be rejecting H0. That would mean that we would go with H1, and our sample would be coming from a population whose systolic was above 120. If we fail to reject, then that would mean that our sample, even though it had a sample mean above 120, did in fact come from a population whose mean was equal to 120. Okay. Identify the test statistic. So 124.5, that is our sample mean. And we need all of the digits on these problems. So our X bar, 124.5. Our sample standard deviation See if it seemed reasonable to us. 16.36793. Now, out there in the real world, carrying 5 digits after the decimals, not, yeah, it's a little bit excessive, but if we do any type of rounding here too early or fail to include all those decimal places, then we can get an answer that's close, but they'll still count it wrong. 16.36793. Our sample size, well, it was the 100 blood pressures that we collected. So there's 100 people in our sample. And alpha, the significance level, 10%. Once I write down mu, we will have everything we need to calculate our test statistic. Now, in the setup of the hypothesis test, mu, the assertion was that mu was 120. That's what H0 said. Okay, so we, from here, we assume that 120 is true. Let mu equal to 120. Now we calculate that test statistic. It's like a z-score, so it's the difference between these two means over the standard error. It's a ratio of 2 deviations. When I use my calculator, I'm going to want to put some parentheses around this numerator so that I am sure that it is being calculated like I want. And for the denominator as well. Now, if we had already, okay, so look at how this is different from the example that we studied to begin with. Here they have just given us the significance level. It's 10% at your cutoff, right? So the difference here is that we don't actually know what number this corresponds to on the axis. We don't know what t-value that corresponds to. All we have is the area. So, in order to make sense out of our test statistic, once we get it, we will have to find that p-value. We'll have to find the area in the table past the test statistic, and then we can just compare it with this area. Right? Because if this area overlaps that one, then it was a good educated guess. If it does not overlap, then it's not. But we will need to I will make us say that analysis of what the p-value stood for, so that way we can be in the habit of understanding that that p-value is a probability. All right, I'm going to compute mine. You compute yours.
I don't know how to find it. I don't see the parentheses on my calculator.
Are you using the
Oh,
Google?
you know what? No, I'm using my. I see it now.
You see it now.
Yeah.
Then you turn it sideways. Yeah.
Okay. So.
Now, the number that we're getting here is like a t-score or a z-score. So 2 digits after the decimal is all you will need. So the t-value that I'm getting is 2.75. You got yours? Okay. Riley, you got yours?
So, yeah,
What'd you get?
1.33.
Sounds reasonable.
After my 120, though, I have to add another parenthesis.
Yes. So that closes off your numerator. You now have your numerator there in these parentheses.
And now I can divide.
And then you hit divide,
Okay, and then I put in parentheses.
another set of parentheses. So that way the overall format is numerator, divide by denominator. I will go to the T calculator.
And then once I do my numerator for the bottom one, when I do the square root, hit the square root first, then put 100, right? Then close it.
You can. Don't you know the square root of 100 though?
Well, wait. It's like whatever times whatever equals 100, right? Is
Indeed,
the
yeah.
square root. So 10.
10.
Okay.
So you could just skip that part
Okay.
and just say divide by 10.
Okay, just 10.
Save you some button pushes.
Cool.
But yes, if it was some weird other number, square root of 127, then yeah, you would just type in S, you would hit the divide key, you would type square root of 127, and close your parentheses.
Okay. And then I got a number of 0.41243.
Okay.
Okay.
2 digits after the decimal.
Okay.
Okay.
0.41.
So now I'm going to go to my T calculator.
Is it the StatCrunch calculator?
Yeah. StatCrunch, calculators, T. Okay. Everyone should have had 100 as their sample size, right? Okay, so our degrees of freedom would be
99.
99. Was this a one-tailed test or a two-tailed test?
1.
This was a one-tailed test.
So it was less than, or greater than.
And you all had positive test statistics.
So it'll be on the right side
So it'd be on the right side.
of the equal sign.
This symbol here would be a greater than or equals, yeah. It'll
So
be,
we gotta switch it.
yes. So I want to look greater than or equal to my test statistic.
And then we put the 1.33 in the middle.
Yeah, that's your t-value. Mine was 1.75. And it shades the area in the tail past the test statistic. That's my test statistic right there. If this had been a two-tailed test, then I would want to, in my mind at least, visualize another one over here. If you think back to that very first drawing we did, if my test statistic was coming out in between these other two areas, then it was a good estimation. With the more modern strategy, that's actually very powerful because then this area has an interpretation as a probability. What is this the probability of?
That it was you would be wrong if the mean was below 120, something like that. That's the probability that you're wrong if you
do what? If you reject it.
If you reject it.
So here, this area, 4%. I've got 4% of the area. So That's pretty low. That's pretty low. If I reject H0, there's a 4% chance I'd be wrong. All I need to do from here is decide if 4% is low enough.
Yeah, when I go to the 5 does it matter? Just because my numbers are different?
It's just because your numbers are different.
Okay. I was just making sure I did it right, because I did lost some. I just wanted to show you to make sure I'm right.
So you had 120.58 as your
For me.
from your sample. Okay, that's pretty close to 120 already. It's only just slightly higher. The computation looks good. Okay. All right.
And then that answer.
So then, what is this probability here?
My probability is, whether or not I'm correct or not, or whether or not it's, true or not or correct.
Okay, so as a percentage, what is this?
Down here.
Yeah.
It's like 34%.
34% chance that if we reject, we'd be wrong. I don't really like to be wrong, right? No one would. We want to, if we're going to stand up in the crowded room and say, you know what, that's wrong, we kind of want to be really confident, right? And what your result is telling you is that there's a 34% chance that if you did that, if you stood up and said that H0 is wrong, let's look at H0. So we can look at it, see what it is we potentially reject. Just leave that and click right there. Okay. If we come out and say that the mean is not 120, that's wrong, you're gonna be mistaken 34% of the time.
Okay.
That's too high of a chance of you being wrong. Because look, the limitation on how much risk you could take was right there, 10%. Alpha, your significance level, mine was 10%, yours is 10%. Riley, what's yours?
Mine is 9%.
No,
Oh, mine's 0.01.
1%.
On my question, it says 0.01
Okay,
significance level.
Kiara, what's yours? So the significance level is almost always 95, 5%, 1%, 10%.
I don't know if I did this.
So your significance level, 10%.
Uh-huh.
Okay. What do you know? What do you think you might be right?
Okay, so this is what I got. Am I supposed to divide this by 2?
Why would you divide it by 2? So that number is the test statistic. Okay. That's what we put here.
And see, I think this way was really small.
That happens. I mean, it's it happens all the time. Look at you.
I guess
That's
yeah, to put it
That's
together,
okay.
right?
I mean, look at what my test statistic was. So when is it alarmingly? When is the test statistic alarming? I would say if it's more than 4 or less than -4, then I should maybe get worried. Did I do this right? Is their claim just that crazy? But if it's coming out between plus or minus 3, that's a normal thing. Okay. So take this test statistic and type it in here.
so this one's what I put in. It's not really something.
Which one?
Because technically this was this
Okay.
one.
Yeah, that is the test statistic. Yeah.
But I put this in and it was wrong.
Okay. Don't try it again. It'll still be wrong. Let's look at our computation. 124.5 is not what they gave you for your mean. It's 124.38. That's likely the problem. Once you type, Riley, you type in your test statistic. Now that you've got your test statistic typed in,
Find
it's
your
going to want the
p-value.
p-value. The
Which
p-value
the
is
little
this area.
teeny little area that says you could be wrong.
You know,
The
it's
percentage of you could be wrong if you reject it, right?
wrong if you reject. The probability of being wrong if we reject. It's always about rejecting. And this is the probability of being wrong. I don't like to be wrong, so if I want to reject, I need this to be small. And it can't just be small, it has to be sufficiently small. Here, mine's about 4%. The alpha that they gave me was 10%. So, there's my 4% p-value, right? But my alpha being 10% completely covers my p-value. My p-value area is smaller than my alpha area. So this means that you are okay to proceed with your rejection. The p-value will, no matter what alpha is, you don't even need alpha. The p-value will always tell you the probability that you'll be mistaken if you reject. Someone has to make a cutoff, though. They have to say, okay, what's the limitation on the risk we can take if we want to reject? And in this problem, they've said take no more than 10% of a chance of being mistaken about rejecting. And since our p-value is less than that, then we are good to go with our rejection. I can now safely come back here and say that H0, I have evidence to the contrary for H0. We're going to go with this one instead. Okay. They have a little bit more of a formal way for us to state that at the end.
That's a good try to get it.
Yeah, let's try and fix that. So,
Because I'm confused with it a little bit.
yeah, that happens. Let's see, what was my test statistic? I didn't like my test statistic. What did I do wrong?
You're 0.41 or something like
Yeah, I don't know what I had. Mine is 2.75, not 1.75. That means I also typed it in wrong in my calculator here. So let's fix that.
that. All of those, yeah, I'm like, yours is so different from what I got, the 0.341.
That's okay. I mean, it's all randomized. But because I have an even bigger test statistic, then it goes further away from zero into the tail, making this area even smaller than it was before. So now there's an even more slim of a chance that I could be wrong if I reject. In fact, it's less than 1%. 0.0035. My p-value is 0.0035.
You can basically tell them that they're wrong.
And I'll be really
You'll
confident.
be really right.
Yeah, I'm very much confident in going ahead and saying, and rejecting. Yeah, because that p-value is so small. 0.00.
Well, now how do you find the data to make you right then? Is that what else is that the other part of the homework?
So what did we find? We found we didn't. We're not looking for if some to show anybody's right. We're looking for, can we find evidence to discredit that claim?
Okay, so we're just looking to discredit the claim, not to who's right and wrong.
Yeah. And if we find evidence to discredit that claim, then we'll present it, we'll reject and present our evidence and say, you know what, they're wrong. If we don't find any evidence to discredit their claim, then we sort of just pack up and leave and say fail to reject. Failing to reject is almost like doing nothing. Failing to reject, you haven't shown that anybody's right. You don't really know. You definitely didn't show that H0 is right just because you failed to reject. All that you have said is that I don't have anything that contradicts the claims made by H0. All right, state the conclusion. This is the tricky part. My p-value, extremely small. This is my probability of being wrong if I reject. Because this probability is so small, I will reject. Let me make like a flow chart for us here. So your choices are to reject H0 or to fail to reject H0. If you reject, the next thing that you will always say without fail is that you have the evidence. You have sufficient evidence. Your sufficient evidence is the sample data. Because from that sample data, you were able to calculate your test statistic and your p-value. And so your evidence is the sample data. And because you have decided to reject based on that small p-value, then the next thing you're going to want to say is, okay, so I've decided to reject. Well, then I'm doing that only because I have this evidence. I wouldn't stand up and reject if I didn't have the evidence. I want to be confident that I'm doing the right thing. So then, if you fail to reject, it must mean that you do not have sufficient evidence. In either case, the part at the end is the same. No matter if I rejected or failed to reject, I'm going to end up saying one of these two things about my evidence. But this will always lead us back to the alternate hypothesis. If I reject H0, then I have sufficient evidence to support the alternate hypothesis. If I fail to reject H0, then I do not have sufficient evidence to support the alternate hypothesis. Now, supporting the alternate hypothesis, there's a synonymous statement there that's even more obvious. And the assignment likes to try and trick you by switching it up sometimes.
Oh my God, you just. Now, is that supposed to be a 0 or a 1 back there? Down, reject.
This is a 1. This is a 0.
Okay. Reject.
But look how obvious this statement is I'm about to tell you. If I reject the initial, it's because I have evidence to reject the initial. Right? But if you rejected the initial, then that means you're supporting the alternate. Okay? So you need to be prepared to say either one.
Yeah, mine was fail to reject.
You're going to fail to reject, so you do not have sufficient evidence to support the alternate.
What were the numbers to make it fail?
Basically, mine was a 1% significant level. So I had to be below a percent, and I wasn't.
Here I have a very small chance of being wrong if I reject, so I'm going to go ahead and do it. That means I do have evidence. There is sufficient evidence that the alternate, that I can support the alternate. Now, to know if I should, to know what I should say here, I have to understand, are they talking about the alternate in this last statement? And they are. That's where the systolic blood pressure was greater than 120. That's the alternate hypothesis. So I would say support. Later on, in a different problem, you may have to read this carefully to see if they have restated the initial, in which case you would be talking about rejecting it. Okay. All right. Well, they go fast after this. So on to number 7. Let's have a look.
Mine was wrong.
Yours was wrong. Which part?
I got the same number. It just says one of it's wrong, but mine 0 is less than that 10%.
So 34% chance that you'd be wrong if you reject.
Or more than 10%.
Yeah. That's way too high of a
So then I would
likelihood.
have to fail to reject.
Yes, you would have to fail to reject.
Oh. And then it's not supported.
Watch out for that. So if you fail to reject, then you don't have the evidence.
It's not.
Supported. Right. The last part is always support the alternate, no matter what we did.
Okay, because mine's over. See, I'm thinking this is 0.34, so it's 34%.
34%.
10, okay.
Yeah, because it's a probability. It can only be between 0 and 1, right? Yeah, a good perspective on it is to just recast it as a percentage chance of being right or wrong. In the next question, they don't even have a story to go with. Oh, yeah, they do. The story is student course evaluations. And they've just told us what the summary stats are. So I would want to calculate my test statistic. First of all, though, I guess I'll answer this first part. What are the null and alternative hypotheses? Well, I need to look at what they have asked me to test. And up here it says, let's test the claim that the population, if I get this to work, test the claim that the population of student course evaluations has a mean equal to 4. Now they did not say test if the claim was less than 4 or greater than 4. They said test if it's equal. So our interpretation of that should be that we want to do a two-tailed test using the not equal symbol. They didn't say less than or greater than, so I'm not going to use a less than or greater than. I'm just going to check and see if it's different from 4. Okay. So my hypothesis test will get set up like this. So I'll be doing a two-tailed test. Does that make sense?
Yeah, I was just seeing they kind of look the same. I was seeing what the difference was. Because it's just equal or, it's equal to, okay, or great. Yeah, equal or equal.
Or not equal.
Okay,
Yeah, you should read this as like different from. Mu is
okay.
different from 4. So it either is 4 or it's different from 4. That's a nice dichotomy. Calculate our test statistic. So to do that, I would need just these handful of numbers. So my sample mean is 3.92. My sample standard deviation, 0.63. And how many of these evaluations are we looking at? 98 of them. And we're assuming that mu is 4. Make sure you use the numbers in your problem. Finally, I'm going to note what my significance level was. Here, alpha, 1%. So they've really tightened the threshold on how much risk we can take and to reject. 1%. So I'm needing a p-value less than 1% if I'm going to go ahead and reject. So I can say alpha equals 0.01. And this is everything you need to do your hypothesis test.
What was on the graph? The DF number was something minus 1. Was it n minus 1?
It's n minus 1. Yeah. So my test statistic would be, let me note the formula again. X bar minus mu over the standard error. It's a two-tailed test, Riley, right?
Between, huh?
Okay. So you can do that, but it's going to shade the area in between when really what you're wanting is the area in the tails. So the area that it gives you, you'll have to say 1 minus that.
1 minus.
Because what was the p-value in a one-tailed test? It was the area in the tail past the test statistic. Well, now, because it's a two-tailed test, not only do you have your test statistic, you have the negative of your test statistic. There's two tails. I need this tail area and I need this tail area.
Oh, so I just found on my test statistic, my number was minus 2.30 or negative 2.30.
Okay.
So I put negative 2.30 on one end, and 2.3 on the other end.
And it's going to tell you what the area is in between those two.
Yes.
But that won't be your p-value.
Yeah, because I need the ones on that.
Yeah, so you'll have to say 1 minus that. There is a different way to do it. You could just calculate one of those tails and then double it. It's the same thing.
What's the square root of 8?
So I'll just do the standard.
So
one
that's the-
just for my
So in that case, you're going to want to type that in.
So that when I did, I did 0.59 divided by, not the square root and 89. That's it.
Okay, so hold on, come here.
Both in parentheses, bottom and
So
top.
Yes.
I did 230. This would equal.
Okay, so you have this.
So I have this one.
This is half.
Yeah, that's just
Feedback.
this one. Now, if this was, I'm gonna just write this down. Now, if I just change the sign, I'm doing greater than, right?
Then by symmetry, it's going to be the same area, right?
Yes, it is.
And so if you add those two together, it'd be identical to
So I
just
can
multiplying by
just
2.
multiply this. Okay, so
Exactly. Yeah.
all right.
So you just multiply it by 2 for a two-tailed test. Kiara, you all right? All right, here's my test statistic. So I get minus 1.26.
You said that, I'm gonna make that, think of that as a percent.
Your p-value.
So I'll keep that.
So my p-value I got to be 0.024, which would be 24%.
No,
Be 2%,
yeah,
2.4.
2.4%.
So I would say
You-
reject it.
So you would do
There
this.
is evidence.
Hold on.
Right?
You would say, okay, if I reject it, there's only a 2.4% chance of being wrong.
Yes.
Is that low enough?
For mine, yes, because they use a significance of 10%. Okay. So I have sufficient evidence that I
Yes.
can reject it
Yes.
because it is not correct.
What is that last part?
It says
Remember, it's
evidence to conclude that the mean of the population of student course evaluation is equal to 4.25. Is correct or is not correct?
okay. Is the initial or is the alternate talking about that mean being equal?
No.
That's where you're. So this is one of those. This is the part of the problem where you're having to read that statement and understand: are they talking about the alternate hypothesis that I want to
Well,
support?
they're talking about
or-
H0 or
or-
H0.
Okay, so
That's
they're
the
talking
initial.
about the initial.
Yes.
So it's that silly interpretation where I reject because I have the evidence to reject.
Yes.
You know what, that's where I messed up. I put this instead of that, so. Minus 16.5, right?
Mhm.
And then I do the calculation.
Oh, math.
Did you get it? Well,
Yes, I did.
ooh. So down here in that denominator, you're going to need to put more parentheses. So back up. The overall format will be some parentheses, divide, more parentheses.
Oh, so divide them more, oh, yes. Divide by, perfect. I gotta use this phrase.
Did you put it?
Parentheses.
Okay.
89 parentheses.
Square root? No, back up. Square root?
Divided by parentheses.
Yes.
Square root for 196. Isn't that 13?
That's 14.
So 196 square root is
Put the negative in, this,
Yes, you're going to put the negative. To 2 decimal places though. Okay.
yeah.
Now what?
So now.
Yeah, you use that StatCrunch calculator, which should already just be open. You didn't even have to close it. Make sure you put the correct degrees of freedom. There's a different T-curve for every different possible degrees of freedom.
What was yours? Mine 0.1, that low, that was it, that's that percentage, is my degree of freedom.
Your degrees of freedom is n minus 1. Remember the story of the borrowing pencils? The last person to come up here and borrow a pencil had no
So if it
choice.
was 89 was my number, my sample, then it would be 88.
Right.
didn't do that last time.
Yeah, we did that last week.
I have like 99% or 99.
Big move for this person.
One less. 88.
All right, I got half of my p-value here. 0.1053.
Riley, you silly goose.
All right, help me real quick making sense of this p-value. It's 21%.
What's the, were they allowing, what, was it 10% for you?
Yeah, it doesn't matter. Tell me what's this the probability?
That is the probability that you would be, if you were, that's basically you have a 21% probability of being wrong if you rejected their claim of H0.
Yeah.
Cool.
I got it wrong.
Carrying with you that interpretation of the p-value is really handy. What is this?
My symbol is it with the negative?
So, you got your test statistic right, yeah? But so I understand that minus 1.439 is more accurate than what they said was the correct answer. However, the structure of the homework needs you to use the very same number. It's very close, minus 1.44, but it is different from minus 1.39.
So just rounded.
Or minus to the two decimals, just like what we typed in for our test statistic. Okay.
And then my symbol's right?
Yes. No, it's to three decimals, right? 0.077. But look, 0.077, that's just half of the p-value here.
Okay, so that's what I put, and then it was wrong.
Is this a one-tailed test or a two-tailed test? So because it's a two-tailed test, that picture that we were just looking at, of 0.077, it's just one tail.
Mhm.
That's one of them.
Mhm.
The other one's over here with the same area.
So I just switched the sign.
Good, you're gonna get the very same area. You're gonna get the very same area, right? It's a
Yeah.
symmetric curve.
Uh-huh.
So this is half your p-value. This is half your p-value. The other half is over here. Well, now we have to switch it back out. This is half your p-value.
Mhm.
That number is half your p-value.
Oh, so just times it by 2.
Times it by two.
Okay, 0.7.
0.0767 times two.
You said 0.07 times 2?
67. 0.0767, 4 digits, and then round afterwards. Okay, so 0.153. There's a 15.3% chance of what?
There is a 15% chance that it could be, the H0 would be right. I keep getting that mixed up.
What would X bar be in this situation?
It's a 15.3% chance
Uh-huh.
that if you reject, it will be the wrong answer.
So, I got this one. We're gonna have to do all that stuff.
So you
I
have
found the
some raw
standard
data.
deviation, and I got the N. This is N, would that be the N for this?
That is it.
10.
Yes.
Saying that, I don't know what X bar is.
Well, what is X bar though? What does that symbol mean to us? It's the sample.
That's a sample population or something? No. Sample mean?
Sample mean.
Okay.
It's the sample mean.
So, I have the mean right here.
All of these are sample statistics, so that's the sample.
This is, oh, okay. Which is,
Kiara, you
So if mine's 15.3, then I would fail to reject because I have 1%, so that was just way away from 1%.
Yeah.
So if there is sufficient evidence, since I proved that,
No, you're failing to reject, right?
yeah, so it's
If you're failing to reject, then like the only time every time our evidence is strong, we're rejecting.
okay.
They go together, right? You're rejecting, you have strong evidence. You would only, so I'm only going to reject in the presence of strong evidence.
Okay.
And every time I reject, I must have had strong evidence. So, it's when my evidence is weak, that's when I have to say, whoa, I can't reject on this. I'm going to have to fail to reject.
in my question, this 14, that would be the little maybe thingy, right? That'd be this number, the 14 right here, would be this one on the equation, right?
Yes. Yes. And you know that because look what you put here.
Okay, that's just double checking.
Yeah.
You never know with math nowadays.
When you said we have two tails, is it because we have this one and this one, the HO and the H1? That means two tails?
You have two tails because of the inequality on the alternate hypothesis. Right? They said test if it's equal to 3.75.
Okay, and that would make it a two tails because you're doing equal.
Because our alternate hypothesis was just different from. Yeah. Because if I'm going to say less than 3.75, well, that's one of the two. If I was to say greater than 3.75, that's the other one. If it could be less than or it could be greater than, that's the same thing as just different from 3.75.
Well, I remember that.
If a number could be greater than or less than 3.75,
Okay.
then it is the same thing to say it's just not equal to 3.75.
So now I'm gonna have a one tail, but my next one says less than.
Correct.
I'm only gonna times it by two.
Correct.
Okay.
No, you're not going to times it by 2. Yeah.
So I need to make sure I can know the how.
It'll just be when you type in your test statistic, that'll be your p-value.
Okay.
So questions 9 and 10, Riley's already up at
We're
9.
skipping 8.
I mean, you can do it or not.
It takes me so long, I wanna keep up with where y'all are at, so I don't fall behind.
It's just that on 9 and 10, it didn't give us the X bar. It didn't give us this.
So we
We're going to
figure
have
all
to
that
construct it. Yeah.
through Stack Crunch like you used to.
Mhm.
Okay, so I'm just
Number
not.
nine. All right, number 9. We have lead concentrations in some medication. Right away, I'm going to need to know the average lead concentration, the standard deviation for the lead concentration. I can open this data in StatCrunch by clicking those little boxes on the side. Did you get it?
I did, my mind is blank.
It's those two little boxes right there. It opens the data in StatCrunch. I can say summary stats columns. I tell it which column, and I just hit compute. Gives me everything I need by default. So now I have my the average lead concentration in those 10 medications. And if you are really on top of it here, you can look and see that next to the standard deviation they've given you the standard error. The standard error is the S over square root of n. So you can save even more time in your computation because this number right here is your denominator of the test statistic. Does that make sense?
So I don't even have to write down the square root part of it. I can just put that. I can just do the what is it? X bar minus mu divided by the standard,
The standard error.
Wait, say that again. I missed it.
X bar.
If I took this standard deviation divided by the square root of 10, I'm going to get this number here. It's called the standard error.
Oh,
Well, we were calling it something else, huh?
No, that's what we were calling
So I can use that number instead of calculating.
Yeah.
2.04. That's right.
And we had this advantage here that StatCrunch would do some of the lifting for us because we had the raw data. Right? In the other problems, they only gave you the standard deviation and the sample size, so you have to calculate. All right, they're wanting me to check and see if lead concentration in these medicines is less than 14 micrograms per gram of medication. All right. Regina, you would still need to use parentheses in your numerator. Okay. Okay. Riley, what are you grumbling about? What
I just
happened?
like to grumble to myself.
You just like to grumble to yourself.
It's honestly, it's part of my process of like figuring things out because I just kind of like, complain to it and just like yell at it and voice my thoughts on it, and then I just figure it out. It's really weird. I don't know why that happens, but it just does.
All right, so I was able to get a test statistic of minus 1.44. What are you getting wrong?
My test statistic, that number that I got, I put it to 2.04. It's saying it's wrong.
Okay.
I'm using my standard error right on StatCrunch.
I did.
Just look. I got 2.04. Well, when I put it in, it's wrong.
No. The standard error is,
The test statistic.
it would be called the test statistic. The test statistic is x bar minus mu over the standard error.
Oh, so I gotta put that.
The standard error is just the denominator.
So now I need to.
Mu
It's two, right?
is what the claim was in our hypothesis test. Okay.
Negative that by.
What did they say the lead concentration would be in these medications? 14. In fact, if you just look at the initial hypothesis, it says mu equals 14.
It does, okay.
So then that means that that's the same mu you would use over here, 14.
So 14
It's
minus.
no. So it's x bar minus mu. Yeah. That's our test statistics. So you can see why it's good to, at least while you're starting out, write down something in the beginning to guide you.
Right, because I keep going back to my old notes and then I'm getting mixed up.
Yeah. It's easier to look at this than it is to look at some numbers. Sample mean minus the population mean.
Okay, so my sample mean, that's 11.8. 0.54, do I round it to 2?
No, keep all those digits.
Parentheses. Well, that's already the answer for it.
That's the numerator.
So I don't have to put anything else though.
You do. You have to divide by the 2.04.
Well,
You have to do
parentheses.
everything the same as you did before, with this exception that you
Already have
a
that.
little step saved, yeah, because the denominator is just this number.
And I don't have parentheses, do I?
It's just one. It's just a number. Right? There's nothing to. If you hadn't put the parentheses on the numerator, it would be a problem.
Now, the answer would be 1.44.
Is that what that says?
Negative 1.44.
It's very oddly the very same number I got.
Yes.
Okay.
Okay, cool.
All right. Now what?
Now I need to get the p value.
You need to get the p value.
I use that percentage, I go to stack times.
Mm-hmm.
0.01 up here, right? Under the DF, do the 1%. No?
That 1% refers to your alpha. That's an area. Our degrees of freedom is, you have to remember like the story with the pencils.
Mhm.
I have 3 pencils to loan, there's 3 of y'all. Every time someone goes up, they have the freedom to make a choice, except for the very last person who
So
goes
I'll
up.
be 13 since mine's 14.
You get the last one?
Yeah, I'm on myself.
And then my symbol would be greater than or less than?
Is your test statistic a positive number or a negative number?
Or negative?
So I want an area in a tail, right?
Mhm.
And it's a negative number
So it's gonna be all the way on the left side.
on the left side.
So then my arrow needs to be pointing towards the left side. That's where I
Yes.
get mixed up. Huh?
Yes.
And I get
Points left, less. Right. Okay, so is this a one-tail test or two-tail test?
One time.
Then that's the p-value. All right, let's take 10, and when we come back, we will do the other kind of hypothesis test about a proportion, and hopefully it won't be.
No, wanted proportions.
I know, but
Those were terrible.
You know, which one?
The ones we did last week that were just absolutely rattling our brains.
You know what's
Getting
funny?
shaken like a rag doll.
Is when I have your help here and you're like right here, but then when I go home, even looking at my notes, when I try to do it, I'm always off somewhere.
See, that's why you gotta finish it before you go home.
I'm so slow that I'm the only one here.
I mean, that story is the same thing that I would have said when I was in school. I mean, it's like I would be
So
telling
what
my
did you
professors the
do?
same stuff.
To like do it on your own. Like when I'm on my own, I'm like getting it all wrong. When you say practice the
It's a
word,
struggle.
I practice. And it's still wrong.
Google it at that point. Just Google it. You know, videos on how to do it. I don't know.
But
That's how I
literally,
got-
if you start
That's low
like,
key how I got through chemistry.
1, 2,
YouTube
3,
University.
8, 7, right?
That's how I got through chemistry.
Just make sure I read that.
And I even barely got it.
It wasn't negative. So 1, 2, 3.
Get it up.
Why should be 13?
My sample size was 14.
You really have 14 numbers?
See? That's the mean.
That's the mean. How many numbers are right there?
Oh, you mean all these? You gotta count these, huh?
Yeah.
1, 2, 3, 4, 5, 6, 7, 8, 9,
It
10,
says it
9.
on the, if you do the stat crunch thing with the means
says
and
it.
stuff, if there's literally a column that has N on it, and that's the number for it.
But you've already counted them by hand, so you don't even need that. There's 9 of them.
Was
But there it says it was 10. In for number, and it's your sample size.
So I'm gonna assume
this is where I get caught up on these.
Yeah, everybody else too. What are you gonna assume, Ronald?
I'm assuming that questions 1 through 5, we're gonna have to do last week's stuff with this week's stuff.
And I suck when I got
And
What do the results suggest? So what was your
I hate
result?
being smart sometimes.
I just really want
I just don't know what to do.
Okay.
You don't need that?
So,
I just forgot. My dad had done that. Probably
reject.
stuff that second I did the quiz.
Now, anytime you reject, it's because you have evidence, right? So let's look at the one that says that there's strong evidence. There is strong evidence that the mean is less than
I got
1,000.
the
That's
numbers
the
right,
alternate
but it's not
hypothesis,
good.
right?
But
But
And
there was
I was like, you know,
the
it's taking
one
the-
car seat in the sample above 1,000, which is where that's where the safe car seats are.
Honestly, I don't think I'd be much on
Isn't that what C says?
Okay, so since it is not 9%,
Let's take 10, and when we come back, we're going to do.
Suffer.
that part, like you give 9%, 10%.
Do it.
Yeah, I always forget what to put it. Okay, so then if mine is really 9.2% pretty much,
9.2% chance of being wrong.
and then
That's pretty low. This is low enough.
1%. But it's not low enough.
It's
to
not
be
low
looking
enough.
At 1%, so that means I would, wait. If I'm certain that, I would fail to reject
You
that.
would fail to reject. You have evidence?
There is not
You do not have sufficient evidence of what?
of them being 1%.
Of supporting the alternate
Mhm.
or rejecting the initial. It's the same thing.
So then it says, so it warrants rejection.
Wait. Is if this is what you're supposed to put, then the rest of the statement would be saying initial hypothesis. Correct. Because right there it says less than 14. Less than 14 is the alternate hypothesis.
Okay, great, okay.
All right. See you in a few, and we will do 1 through 5.
Excuse me. Right.
The some of this terminology did come back. The T line, the Z.
Yeah.
And deviation. I'm like, oh goodness.
For some, I guess it could be traumatic. For other people, it could be.
I needed you to teach us. You will get through it, so just. You all coming along good in the class?
Yes.
Yeah. Our days of stats were like, oh goodness.
It makes it easier that there's not very many of us in there.
So that's kind of good to hear because he wanted to add another math course on site next term, and I told him it'd only be like 4 or 5 students. And he said, but it works out.
It really
Because you
does.
don't have a full class of questions. By the way, I'm sorry, I'm Dr. Lasani, you're gonna be, for attendance, so, but yeah, and he said, but it works out, because he can provide individualized help when needed.
It definitely does help because I'll tell you what, if I was taking this online, I would be so screwed. Oh my god, I would be so screwed.
That or not even being able to ask the questions that we need to at that time.
Okay, this is good feedback, seriously, because it was almost like, no, because it'd only be like 4 or 5 students in a course, and I was like, every course doesn't have to have 20 students, is what I'm saying, and I guess you're saying this course is good.
Yeah.
With how many's in there?
100%.
You have a higher success rate.
Higher success rate, that's
Yeah,
exactly
grades
what
will
the goal is. Okay, well, that's good feedback, thank you. All right, you all enjoy.
You
Thank
too,
you.
man. Have a great day.
So.
Are you doing number 1 and 2?
Yeah, I'm doing number one.
How do you do it? What are you doing?
Well.
Oh, we have to do what? What do we gotta do for these questions, homie? What the fuck?
Well, I'm just doing because it says less than, so I'm going to choose the one equal. Well, it says equal, so I'm going to choose the one that's equal. This is the only one that is, we have to say equal in this one, for this one is equal to, so I knew that one was this one, and then we're going to test the TS. So I'm just going to do the same thing and see if I can
See
do
if you do it. Do it. Guinea pig it.
it. See if I get it right.
See if you get it right. If you don't, you don't. Fuck it. Life goes on.
It does.
It's my philosophy of reason.
What time do we get out of here? 4?
Yo, you want to stay after and do the midterm together?
Yeah.
Hell yes. Hell yes. So,
Did you end up doing the quiz again?
Nope.
Or you left it as is?
no, I let it be. I let it be who it is it's supposed to be, an 80%. Because I know if I did it again, or I would get it wrong.
That's what I did. The first time I got an 89. The second time I took it, I got an 80. I said, nah.
Nah, 80's fine. 89's what I'm getting.
Right.
Nah, fuck it. Whatever. I don't think this has enough information for us though.
Let's see.
I can't breathe. Something going on in my heart, man. Every year, as I get older, something new don't work. Like a half a century, I tell people, I'm half a century old, I'm about to die. I can't breathe. Stairs would help me. I don't see why we get so confused in this. Because I be writing notes, and then when I get home, what's confusing me is that one less than. Is it always? It's always gonna be one less than your actual number every time you do a problem?
For the DF?
Only for the DF? So DF. And what's DF stand for again?
I have no idea.
DF. DF is always number minus 1. Yeah, I gotta do that quiz over. Oh my God, I got like 30 something. Well, what it was I had got some of them, but it was like, you know, it was like 2 parts. Probably got like 1 right and then an X on the other part.
Right, I hate that.
Yeah, right? That made my score so low. What does DF stand for again?
Degrees of freedom.
Degrees of freedom. I'm trying to remember when do I take that 1 away from the number.
Degrees of freedom. It's like in the
What happened?
It's like a scary movie when you said
Yeah,
right.
you just stand here.
Just stand
Oh.
there.
Oh,
I just heard a little knock. I was like,
I didn't hear it, but something rolled off your desk.
yeah. So how many dimensions does our universe have?
Infinite.
Infinity.
No.
Oh, the infinity.
4.
How many?
Oh, what?
You can go up.
Oh.
You can go this way. Right? In space. In space, you have 3 dimensions. And time is the 4th dimension. 4 is 4
Oh,
dimensions.
I didn't know that.
Time is the 5th dimension for me to start.
So there's 4 dimensions, but we only have 3 degrees of freedom. Because when it comes to time, you don't have any choice but to go this way in time. But you're free to go,
Left, right, upward.
yeah, to go forward or backward. That's one direction. Left and right, it's another. Up and down's a third. Okay. Degrees of freedom.
Well, according to Marvel, those are universes.
Huh?
Those are universes. They have like multiple infinite universes or weird. I don't know.
That's different. That's the question of how many universes are there. That's going to be uncountably infinite.
Yeah.
Yeah, it's continuous.
Actually, I was dating this one girl for a little bit. She's like going to school for like theoretical physics or something. And she was telling me they had to use like seventh dimension math or something, but like for certain other types of math and physics, you have to use like 5th dimension math because it doesn't work with 3rd dimension math. And then honestly, as she was telling me this, I just kind of told her to stop because like you're just hurting my head. I don't know there was different dimensions of math.
Oh yeah, there's as many as you want.
That makes no sense.
So you're a mathematician?
Yeah.
What does it mean to be a mathematician?
It's you freaking.
Which means I
Someone that
know.
loves math?
No, people can love math but not be mathematicians, right?
What's a mathematician?
Someone that has studied like all the math.
You're good at all math. Really?
What's your favorite kind of math to do?
Synthetic geometry.
I don't know what that is.
That's the thing.
Synthetic geometry. How can you have synthetic
Fake
geometry?
What
Is
does
it
that
fake
entail?
So you're familiar with like the coordinate plane. You know, it has the x and the y axis, and you know there's that point right there, and it has the ordered pair. You know, 3, 2, right? So this is the Cartesian coordinate plane. It comes endowed with this structure, that this is the number line. It consists of all these numbers. They crisscross, and you can talk about the address of that point. But if I start with absolutely nothing and just have a geometrical perspective, then I don't get that structure. I would just have a plane, and I would start with a point, and then all I would have is that there's this other point, and from just this basic stuff, I would have to construct the real number line and the coordinate plane and get the trigonometric functions and get the inner product.
Just from getting from 0 to 8 from one line.
Yeah.
What?
Well, so yeah, I mean, because then I could have this other one here, and I can talk about, well, what is a fraction? I can say that if these two things are parallel, if those two lines are parallel, then I would have that these two fractions are equal to each other, just like 1/3 is equal to 3/9.
Oh, it's just because it's more.
I know, you simplified.
It arrives at, what it does is it puts everything that you know about the real number system on a geometric footing.
That's kind of bad. Why did you want to do that? You just could do like numbers? It's challenging.
Yeah, it's just geometry. Mhm. Yeah. So I also studied calculus on manifolds, and so in that perspective, the universe is a 4-dimensional manifold because you have 3 spatial dimensions and 1 time dimension, and it gets really complicated after that, just as
I feel
complicated
like
as
that's
you
the
go
kind
on.
of math that they don't really use a whole lot of numbers.
No.
Because as math gets more complex, the less numbers you use, and that just is, I don't get it.
That's my weakness. So what subject?
It's
was
because it
your
gets more and
weakness
more
in?
general. The more generalized you want to make it, the less numbers are involved. So what's up?
What subject is your weakness?
Topology.
What is it?
Topology.
What's topology?
The topology is the study of spaces. So, like, there's, so just for an example, I mean, if I was talking about, this square, then there's lots of different spaces going on here. You could have the region inside the square that does not consist in its border, or you could have just the border without the part in the middle, or you could have both of them together, and then you can start to talk about, well, if it didn't have the border, like if it didn't have the border right there, then you could approach that edge. You could keep getting closer and closer and closer forever, but never actually reach the edge. You could just get closer and closer. But whereas over here, you eventually hit the edge. It's strange. Okay, test statistic for questions 1 through 5 has largely the same format. We make an observation about p, little p.
Probability.
No, it stands for proportion in this case. It's a lowercase p. It is the sample proportion, right?
And the big P is the population.
The big P is probability. Sorry, I made a mistake here. This is little p hat. This is the sample proportion. When it doesn't have the hat, it's the population proportion. This would be what they're making their claim about. So it's just like x bar minus mu.
These will go.
Yeah. Except
So
for
instead of x bar minus mu, it's p hat minus p.
yeah. And then it's over the thing that's like a standard deviation. It's the square root of p times 1 minus p over n. Okay. So everything else is going to be the same. All the process is still the same.
But we just gotta
But it's
put
not in
numbers.
parentheses.
Yes, it
Eventually
is.
will.
They're just, they don't need to be,
Right now.
when I write it like this, they don't need to be written, but your calculator doesn't understand this. Your calculator would understand this.
Okay, let's just. Okay, so p hat is the sample proportion,
Yes,
and then p is the proportion,
population.
population proportion.
Yeah.
So in our question, suppose a random selection of 100 colored candies. That's p. Is 100?
It's in.
N is 100. Okay.
Yeah.
And then 28% of them are blue. Candy company claims that the percentage of blue candies is equal to 21%.
Okay.
Use
So they have said to you that P is
Which is the-
0.21.
wait, P was the population proportion.
Yeah. But what you observed was that P hat was 0.28. Okay. Your N was 100. So your test statistic would be
What number is this?
So it's going to be 0.28 minus 0.21 over an entire square rooted of 0.21 1 minus.
so when it comes to the 1 minus part, I want you to do this. I want you to calculate it.
I could just do 1 minus
Up front.
0.21.
So like 99.
I'd rather you not do that.
Don't do that?
Don't do that.
Okay.
You know it's 1 minus 0.21, right? You're making change for $1. Something cost 21 cents. Someone gave you $1. Let's go ahead and say it's 0.79 and write that. Okay? It will save you
So
headache
we're
in the
not
calculator.
writing 1 minus 0.21 in the parentheses.
I would not
We're just going to do it.
do it. We're going to do it right now.
So 1
First,
minus
before everything
0.21
else.
would be
But how
70.
is 1 minus 0.21 and minus is 0.79?
Add these two numbers together and see if it don't come out to 1.
22 plus 79 is 99. But 99 plus 1 is 100.
21 cents and 79 cents, that's $1.
Yeah.
Can we already square root the number before or n? If it's 100, I can just put over 10, right? Or is that square rooting it twice?
So that would be square rooting it twice if this radical stayed including that 10. On this one, let's go ahead and just put it over 100.
Okay. So how would I write that on my calculator?
In the calculator, you're going to type the following point. You're going to type open parentheses 0.28 minus 0.21 close parentheses divide square root. When you hit the square root button, it opens a parentheses for you. Inside, you will type
0.21 times. You're doing it times.
0.21 times 0.79 divide by 100 close parentheses.
I have 1.72.
You got 1.72.
Alright, now we'll go with a p-value.
So when it comes time to do the p-value, this is a z-score.
Yeah, and then 1.72.
It's a z-score, so you go to the normal curve.
On the T calculator?
normal.
Calculator. Oh, we need, then what would the mean be, standard deviation?
0 and 1.
Okay, so that doesn't change at all?
No.
Okay, we're looking for equal to though. Or does the sign not matter?
The sign does matter. So is it a one-tailed test or a two-tailed test? I mean, the sign matters in terms of
It's a
this is a
two-tailed
positive number.
test. It's a two-tailed test.
This is a two-tailed test, and this is a positive number. So you need to have it looking greater than 1.72.
Greater than,
And when you get that number, it will only be half of the p-value.
okay.
So when I do the square root, I'm doing square root of 21 times 0.21 times 0.79.
You're going to press divide. Now you're close. See how that's the numerator and then divide by that
Square root to reject.
That's it. That's what you want.
So I need, okay, so it's about 1%.
So I was wondering why the parentheses was up here, but not the whole thing.
Because we don't need them. Because multiplying and dividing, I mean, I could take away that parentheses around the 0.79, but I would need to put a little
That's what
multiplication
me,
symbol.
because then I was thinking.
Oh, so it's, we just, for these ones, we're just using a different formula?
Yeah.
Could've just said that.
Equals
Instead of just scaring
That's all I
us.
did. Everything is the same except for
0.49114. So now that is my that is my Oh, we're doing C-scores now. What is
That's
this?
your test. It's a z-score, so we're looking it up on the normal calculator.
Okay, so then, I don't want to know how many of this test should be best. I want equal or greater than 0.23, right?
Well, they've said, so what's the claim? The claim is that it's equal to 23%. They didn't say it's greater than 23%, and they didn't say it's less than 23%. So it must be the one we have picked.
It's crazy because what, this is the same,
It's not the same.
because that's not the.
The initial hypothesis has got to have an equal symbol.
P hat is, P hat was sample probability,
P hat is the probability that you would mistakenly reject H0. Oh, I'm sorry. It's crazy. The p-value is that. P hat is the sample proportion. Yes. P hat is the observed value. When you went and looked at the candies, you saw 28% of them being blue. Right?
now, if I have 248 students are being treated with the
What
drug
is wrong?
that is used to treat pain, and 54 develop nausea, 54
Out of
would be my,
numerator of the,
of the 248, but the P, 54 would be P hat,
no.
or just
P hat is a proportion. What proportion got nausea? Well, it was 54 out of 200 and whatever.
Yeah. So that would be P hat.
What is wrong?
Your numerator's not right.
The 100 here?
Is that the numerator? Numerator is the top of the fraction. This is a fraction that you're typing in and computing.
So what would my numerator be then?
Well, correspond this stuff. P hat is what we observed. Did you observe 23%?
Yeah, total, yeah.
No.
No?
That's their
I
claim.
observed
They claim
21 of the blue.
you observed 21%.
Okay. And then that's there, so it'd be 21 and 23.
All right, I have a question. With my, I just want to see if I set up the my equation correctly. So this
This
was
is negative, by the way.
this was have to do something with this 20%.
That's their claim.
So would that be the P?
That'd be P.
Okay, so it's not 54 minus 194?
No.
Okay, it's 54 minus 0.20.
It's not 54 minus 0.20.
Well,
Think about how weird that, 54 minus 0.20 is practically still 54.
oh, does it want me to find the percentage of 54 people?
You need P hat. P hat is 54 divided by
248.
248. Get that to 4 decimal places.
It's really high.
21.77.
Like we just said.
0.2177.
The correct,
Is the correct answer?
it would be just the negative of this. The curve is symmetric. If all we're doing is, if these two are just switching spots,
Okay.
you're just going to get the negative of this. But you need to understand what you did to have it be wrong here. So
I didn't put it in parentheses.
Wrong.
Sorry. I should close that parentheses.
Yeah. So what does this really say? This says 0.21 here by itself. This is 0.21. And then what gets subtracted? The thing that gets subtracted is 0.23 divided by this square root. But that's not what we wanted. You didn't have your numerator in its own parentheses.
Okay.
C, press C.
Okay.
The format needs to be numerator divided by denominator. That's what a fraction looks like. So you have to make sure that all of your numerator is in its own parentheses.
All the numerator. But not the denominator.
It just doesn't need it. If you're here, the denominator is the square root of all this stuff. So right after I press the divide key, if I press square root, I just put all that stuff in there, and it acts like its own parentheses.
Now, let me just think what I was in my notes. P value was going to the set range, and I needed to know the number was on one less than. So the 99 under
We don't need to do that.
No,
No.
because I'm not looking for
The normal calculator does not need any degrees of freedom.
okay. So I'll just go to that calculator. Nope, that's wrong.
It's the T calculator. You need the normal. Click that. No, yes.
Calculating normal. And I'm not doing between, I'm gonna do standard, right?
It's already on standard.
0.01. And then I'm gonna put this number in there.
No, that's not the right one, right?
It was negative.
It was negative. Negative
So it'll be on
0.49.
this side. Negative. 0.49. And then it would be less than, what is it?
That's a negative number, right?
Yeah, so.
So it needs to be less than to be in the table. All right. Now, is this a one-tailed test or a two-tailed test?
So 1
Really? Look back at your initial hypothesis and alternate hypothesis. Your alternate hypothesis has a not-equal sign.
Oh, okay.
So that means it's a two-tailed test. So then the area that you're looking at there is only half of your p-value.
So you would divide it by 2. That would be the whole number?
No, it's good.
And it's no longer negative.
The p-value will never be negative because it's an error. It's a probability. It can only be between 0 and 1.
So yeah, if you're not right here telling me, no, this or that, I'm gonna be like, where's the P? I'm gonna be looking for the DF and then one negative number.
Yeah, you can be looking for DF all day long, but there'll be no place to put it. Right? There's no place to put it because you're on a normal calculator.
So now we're looking, okay, they're just saying 23%. And I have 62%
Chance of,
being that, I don't know how to word it.
chance, 62% chance of being wrong if you do what?
If I reject it.
If you reject H0.
Okay.
We don't like to be wrong. 62% chance of being wrong, way too high.
Right?
So
then,
I probably should not be rejected.
okay, so federally reject, there is sufficient evidence to warrant rejection of the claim of the percentage we claim. There is not, okay, so there is sufficient.
No, there is not sufficient. If I fail to reject, I do not have the evidence. If I had the evidence, I would have rejected. Failing to reject means I couldn't find anything to contradict their claim. Had I found something to
Because I thought
contradict
this
their
is what I
claim,
found that made it be contradicted because of the 62%.
that 62% refers exactly and only to the probability that you would be wrong if you reject.
Okay. So, oh, this stuff is tricky.
I have a question.
Mhm.
So if I'm doing the one with the nausea,
Mm-hmm.
do I get this percent of this one?
You had 52 get nausea out of 215. So 51 divided by 215, that is p hat.
So 25%.
Do it to 4 decimal places.
I don't understand this question.
51 divided by 215, you got 0.2372, right? Okay. So 0.2372, if I go ahead and compute 1 minus p hat, then that would be 0.7628. I'm going to need those two numbers down in my denominator.
Yes.
I'm confused on this stupid question.
What's the problem?
A poll of 1,012 Americans showed that 47.1% of the respondents prefer to watch the news rather than listen to it. Use those results with the 0.10 significance level to test the claim that fewer than half of the Americans prefer to watch the news rather than read or listen to it. Use the p-value method. Use the p-value method. Use the normal distribution as an approximation to the binomial, whatever how that is.
You can ignore all those extra words.
And so the first part, I got the numbers wrong.
Fewer than half.
So,
If I said 50% of Americans, that would be half, right?
uh-huh.
So P equals 0.5. Or P is less than 0.5. Would be
0.50 be
significant. P equals 0.5, P less than 0.5. That's the two options.
So p hat, or p, and the number is 1012.
I want to make sure I'm starting off.
Well, then
My P hat would be 50.
47.1%
Sample
is,
out of the 207, right? Did I go backwards? That's the sample they took out of it.
Little p stands for proportion. Percentage, if you will. The question becomes, what is the percentage of people that got nauseous in this study?
So 20%?
No, that's the claim.
Oh,
P
okay.
is
so
20%. P hat is how many people you saw get. Not how many, it's the
50
percentage.
would be the P hat then.
No, that's just, 50 is not the percentage.
20?
What did we have?
No,
1?
now you're guessing.
Because I'm looking for a percentage.
I want to, you're looking, but like, what if, what percentage of the time do you get here to campus without hitting traffic? How would you calculate that?
I'm finishing 2 right
Or we have like a 50-50 chance.
That would, if that were true, then that would mean that 50 out of 100 times you hit traffic. 50 out of 100. Here you had how many people get nauseous? 50 out of
207.
207. 50 out of 207. That is p-hat.
Oh, so I have to subtract 207 from 50?
No,
now.
no. I want a percentage.
Oh, you want a percentage, okay.
P-hat is a percentage.
So it'd be 50%.
It would not be 50%.
Suppose your man just with a usage pain. 50 of them develop nausea.
Calculating percentages is a fundamental requirement for a nurse.
What part are you on 3?
My brains,
Yeah, so
my
so
gears are
let's
turning.
go
Give me a
back to
second.
the 50-50 shot.
I'm hoping I figured it out.
How did we get a 50% chance of hitting traffic? Well, to it. The number of times we hit traffic divided by the total number of times we went to work. The part divided by the whole. 50 divided by 100, that's 50%. Well, what if I had done 60 trips instead of 100? 60 trips, how many of them would be hitting traffic?
Is it be 60 out of 100?
No, that would be 60%.
Oh, that doesn't make any sense.
If you got a 50-50 shot of hitting traffic, and then if I only want to look at 60 trips, how many of them are going to hit traffic?
60 trips.
That would be 100% of the time you're hitting traffic. That's not a 50-50 shot. That's 100% of the time.
So it'd be 30.
30. 30 divided by 60 is 50%. To calculate a percentage, you are taking this number divided by the total observed.
So I'll be doing 50 out of 100.
Is that how many people were tested with that drug?
No, 207.
207.
So I would divide that.
I'll say 50 divided by
207.
207.
We didn't do that on the other ones, did
Yes,
we?
we did. We did it last week. For
last week.
p-hat,
Oh, yes, that was last week. Oh, gosh.
the percentage of people that got nauseous is 50 divided by 207. Question.
I don't think I did this right.
24% got nauseous, carried 4 decimals.
Did I set this equation up right? So I got p hat, which would be the percentage, right? That one, 47.1. The p hat.
Okay.
And then the p is obviously 0.50. This is what I wrote. So 0.471. And then I got that. Did I go somewhere wrong?
Is there a divide in between those two? I don't see it.
The fifth brain.
No. Over here.
Oh, right here?
It's going to assume multiplication.
That's what I did wrong. Divided by
So my Q would be 207, right?
stupid square
That's
root.
the total amount.
Is so if that were true, then you'd be saying 207%. Actually, you'd be saying 20,700%. 20,700%.
Oh, I have to count a percent of that too, so